Good afternoon, everyone. Today we're going to talk about the vector cross product. And not too long ago, we went and did a little bit of work with the vector dot product, discussed its derivation, and then worked through an example. And so today we're going to do something kind of similar, and we're going to extend on our knowledge that we gained from that previous video on the vector dot product by discussing vector cross products. Okay, now the very first question we need to ask ourselves is, what is the vector cross product, right? So one of the first things we're going to do today is we're going to discuss the derivation of the vector cross products formula, and then we're going to just do an example of how to compute a cross product of two vectors, and discuss the geometric meaning of the cross product. Okay, so let's begin by drawing a little picture. Alrighty, I've got the formula for the vector cross product up on the whiteboard as well, and we'll discuss where that comes from today, but this is essentially what's happening. Imagine you have two vectors, u and v, that both begin at the origin and go in two separate directions, and they have the angle theta between them. What the vector cross product finds is it finds a vector to which both u and v are orthogonal. In other words, the vector u is perpendicular with the vector a, and the vector v is perpendicular with the vector a, making a 90-degree angle. Okay? And we're going to use the fact that the dot product has its geometric definition defined as follows, where the dot of u with v is the magnitude of u times the magnitude of v cosine of theta. And we know we're looking for a 90-degree angle between vectors u and a and vectors v and a, right? And then we also know that cosine of 90 degrees, or cosine of pi over 2, is 0. So that is where the whole premise behind the derivation for the vector cross product is going to kind of come from. The fact that we know a dot product of two vectors is equal to 0 if they're orthogonal. Alrighty, so let's work in three dimensions. Let's say the vector A has coordinates a1, a2, a3. Let's say the dot product of u with okay, that's actually incorrect. What I should have had up there is that the dot product of u with a and the dot product of v with a is 0. The dot product of u with v is not necessarily 0, so you'll have to just disregard that for now. I apologize. But that's going to be where we begin. And then we're also going to use the fact that the dot product of two vectors is equal to the product of their components summed all together. So that means the dot of u with a is equal to u1a1, u2a2 plus u3a3 if u is a vector in three coordinates with coordinates u1, u2, u3. And then we also know that the dot of v with a is equal to v1a1 plus v2a2 plus v3a3 if the vector a is a vector in three-dimensional space with coordinates v1, v2, v3. Alrighty, so, okay, now, just like we discussed earlier, right, the dot product of u with a needs to be 0 and the dot product of v with a needs to be 0. This yields us a system of equations in three variables, but only two equations. Now, just because there aren't as many equations as variables doesn't mean that we can't find a solution. It just means that it's a little bit more complicated. And sometimes it means that there are multiple solutions to this system of equations that we're given. And we'll walk through how to go ahead and do that. So what I'm going to do first is I'm going to find a way to eliminate the a3 variable, right? Because I want to solve for a1, a2, and a3. Those are I want to find the coordinates for this orthogonal vector here, the vector a, in terms of just u and v. So I can take products of the components of my vectors just like I did when I'm taking the dot product of two vectors and go from there. Alrighty, and I can begin by multiplying the first equation by a u3. If I multiply each part of that first equation by u3, and then each part of the second equation by negative v3, then you'll notice that I can cancel the last two terms. Right? The last term in the first equation is u3 v3 a3, And the last term in the second equation is v3, u3, a3. So using the commutative property, the fact that v times u is the same as u times v, we can conclude that those two will cancel out. And we'll just be left with this expression here, u3v1 minus v3u1a1 plus u3v2 minus u3, I guess that's a v3u2, my apologies. So u3v2 minus v3u2a2 is equal to 0. Alrighty. From this point, what we'll want to do is we'll want to subtract the u3v2 minus v3u2a2 over to the right-hand side. And we're going to observe this very, very carefully. Okay, so at this point, since we don't have another equation to compare it to, since it's, again, like I said, an equation in 3 variables with only 2 equations, what we need to do is we need to observe that the one and only solution to this equation at this point in time is going to be the place where a1 is equal to u2 v3 minus u3 v2, and that is just, notice that is me distributing the negative into the brackets of the term on the right hand side of the equal sign, right? What I can do is I can just imagine that if a1 was that, and if a2 were the negative version of the term on the left, then that should say a2, not a3. Then I would end up with these terms right here, right? So a1 is u2 v3 minus u3 v2, and a3 is equal to u1 v, well, a2, my apologies, u1 v3 minus u3 v1. Yeah, I don't know why there's so many typos in this one this time, but just bear with me. Okay, so we have some terms for a1 and a2. We just need to find a3 now, and we can complete our definition of the vector cross product. Okay, so a1 is equal to u2 v3 minus u3 v2, and a2 is u1 v3 minus u3 v1. Looks like we fixed it on this page. And if we manipulate the first equation up top here, we're going to end up with the equation that says a3 is equal to negative v1a1 plus v2a2 over v3. And remember, we need to distribute that negative into the brackets. And so what I'll do is I'll distribute that negative into the numerator and substitute a1 and a2. Then I'll distribute and arrive here. Notice again that by the commutative property that the first, or the two middle terms will cancel. That's going to leave me here. Then I can cancel a negative, or I can cancel a v3 from each term. So I'm going to end up with u2, or v2 u1 minus v1 u2, and that is what I have for a3. So a1 is u2 u3, u2 v3 minus u3 v2. a2 is u1 v3 minus u3 v1, and a3 is u1 v2 minus u2 v1. That's how we find the cross product of two vectors, is by computing those three components there, in which will bring us to a vector, right? So unlike the dot product, where the dot product of two vectors gave us a scalar, the cross product of two vectors is going to give us a new vector. Okay, so let's go ahead and do an example. Here's our cross product definition. It turns out that we can rewrite those solutions that we just arrived at in a matrix notation. It makes it a little bit easier to compute if you see that it works out in the form of a matrix here. And we're going to compute the cross product of the vector 1, 3, 5 with the vector 2, 4, 6, right? Using the cross product definition, I'm going to arrive at this conclusion here. I'll let you go ahead and do the arithmetic here. 3 times 6 minus 5 times 4 is negative 2, and then on the inside here we're going to have 6 minus 10 is negative 4, but I've got negative 4, so positive 4, and then 4 minus 6 is negative 2, so it leaves me with the vector negative 2 comma 4 comma negative 2. Alrighty, and you can check that vector we computed is orthogonal with both the vector 1, 3, 5 and 2, 4, 6 by taking the dot product and seeing if you get 0, right? Because remember, if the dot product is equal to 0, then the angle between the two vectors is a 90-degree angle and they're orthogonal. Alrighty, and it turns out that that works out. So now what we'll do is we'll discuss the geometric meaning of the vector cross product. And this is going to be a rather long proof as to where the definition of the vector cross product's geometric meaning is coming from, but it'll be worth it, trust me. So first thing we want to make note of is we want to make note that if I was to find the magnitude of the components of my cross product in terms of just u and v, right? I'm going to take my solutions a1, a2, a3, and I'm going to take the sum of all their components squared, right? So I'm going to square each component and then add whatever I get as a result together. And then if I square the magnitude, right, then I don't have to write the square root. So that's where this all is coming from. And if I expand some things out, right, you're going to have to think about how FOIL works and be very, very careful here in order for this to make sense. But I should end up with u2 squared v3 squared minus 2 u2 u3 v2 v3 plus u3 squared v2 squared plus u3 squared v1 squared minus 2 u1 u3 v1 v3 plus u1 squared v3 squared plus u1 squared v2 squared minus 2 u1 u2 v1 v2 plus u2 squared v1 squared. Now that's a mouthful, right? You'll notice that there are a couple of things that I can work with here, right? If I look at just the terms that have squares in them right now, what I can do is I can group them together, and it looks like I can take out a u1 squared from two terms to end up with v3 squared plus v2 squared. I can take out a u2 squared from two terms to end up with a u2 squared times v3 squared plus v1 squared. I can take out a u3 squared from a couple of terms and end up with just v2 squared plus v1 squared, and then factor a -2 out of the remaining terms to arrive here. From this point, we'll just want to pause and start thinking about the dot product's geometric definition again, and you'll understand why we're doing this more in a second here. But imagine if I was to square the geometric definition of my cross product with its scalar product version, right? That's going to leave me here to the point where I get that the magnitude of u squared times the magnitude of v squared cosine squared of theta is equal to u1 squared v1 squared plus u2 squared v2 squared plus u3 squared v3 squared plus 2 times u1 v1 u2 v2 plus u1 v1 u3 v3 plus u2 v2 u3 v3. Okay. Then here's what I do. I'm going to take both of these definitions that I've arrived at here, and I'm going to add them together. You'll understand more why I'm going to add them together here in a second. And I think the reason you'll notice why we're doing this is because a bunch of these longer terms actually cancel out, and we can take those squared terms and group them together like so, such that we have common terms, and it just leaves us here, right? It looks like I've got v1 squared plus v2 squared plus v3 squared. Well, that looks an awful lot like the magnitude of the vector v squared, right? If I was to just have the magnitude of the vector v without the square root, then it's like I'm squaring it. And likewise, if I was to factor by grouping and take that out, then I'd also have a u1 squared plus u2 squared plus u3 squared and have the magnitude of u squared on the right-hand side while the other terms cancel out, leaving me here. From here, I think you'll notice I can subtract the magnitude of u squared times the magnitude of v squared cosine squared of theta over to the right-hand side, factor our magnitude out to be left with this. 1 minus cosine squared is the Pythagorean identity for sine squared. Then I can, of course, take the square root of both sides to arrive at the geometric definition for the cross product. the fact that the magnitude of the vectors u crossed with the vector v is equal to the magnitude of the vector u times the magnitude of the vector v sine of theta. Okay. Now, of course, this can be used to find the angle between two vectors, u and v, given their cross product and their magnitudes as well, using the following formula if we were to manipulate it like so. Okay, so imagine again, for our example, that we have the cross product of 135 with 246. We find that the cross products yield the vector negative 2 comma 4 comma negative 2. And we want to find the angle between the vectors u and v given their cross product. So what I'll do is I'll find the magnitude of the cross product here by taking their components, squaring them, and then adding them together and putting it under a square root. That's going to yield me 2 root 6. And then if I do the same thing for the vector u and the vector v, and then multiply them together, I arrive at 14 times the square root of 10. That eventually leaves me here, right? I'll have 2 root 6 over 14 root 10. 2 over 14 is 7, and then 6 over 10 is 3/5, and I can separate the square roots like so. It turns out that the inverse sine of root 3 over 7 root 5 is 6.35 degrees. And if you watch the previous example where I used the two same vectors but took their dot product instead of their cross product, then you'll know that that is indeed the angle between the two vectors. Alrighty. Well, I hope this was helpful. If you have any questions, feel free to reach out, and I look forward to talking to you later.